Okay. So in order to go back to the time function, unfortunately, we need to consult some Laplace transform entries. Okay, so if we look at a specific Laplace transform entry, and I'm gonna basically make this kind of a side note. Okay, so we have 1 over s e to the minus k square root of s corresponds to a time function. By the way, for k positive corresponds to a time function called complementary error function, ER(FC), and I'm going to define it in a minute, but it's an integral function, okay, of a certain variation of those variables. ERFC is called the complementary error function. The derivation of this correspondence is beyond our scope, but this ERFC of x is defined as 1 minus 2 over square root of pi integral from 0 to pi, from 0 to x e to the power minus u square du. Equivalently, it is 2 over square root of pi x to infinity e to the minus u square du. Okay? So using this correspondence, using this result, we can basically write down the time function xt as m times, oh, by the way, I have skipped something, sorry. Before even that, we need to define which function we are applying at the input, okay? Now, let us consider the step response. Namely, so what we mean by step response is that I am applying a step input, a step temperature input to the boundary. Okay, so I have basically tau 0 t, which is the boundary condition, is m times u of t. Okay, and that means in the s domain, tau 0s is being equal to m over s. So with this, our Laplace domain response xs is equal to m over s e to the minus x s over a square root. Okay. Now with the Laplace transform table result, we can basically say that now the time function is equal to m times this particular error function x over 2 square root of at. Okay. Arkadaşlar benimle misiniz? Bir ses verin.
Ben miyiz hocam?
Buradayız.
Benimle misiniz? Teşekkür
Çok
ederim.
az yukarı kaydırabilir misiniz hocam?
Tabii ki.
Çok teşekkür ederim.
Now let me show you how this thing looks like. Obviously it's not a trivial function, it's like an integral function of time. And that Laplace transform table correspondence is not very obvious. It has been derived obviously by people working on the Laplace transforms. But as long as you know what this function is and as long as you can calculate it, you can now generate the solution. Okay, and I'm going to show you the unit step response for fixed distances inside the slab to show you how it looks like. Okay, so let me show this to you as an example. Unit step response at fixed, that means given distance x inside the infinite slab, and for different x's. Okay, so basically what we are looking at is that we have our infinite slab, right, our previous sketch. It is not bounded on the right hand side end, but we have a boundary over here, okay, at x is equal to 0. This is where we apply this function. We apply tau 0 of t function, okay, is equal to m times u of t. So that means over here at 0, hold on, let me show you like this. Okay, so at over here we apply essentially a fixed temperature with magnitude m on top of the steady state, obviously. Okay, so what's happening is that I want to sketch as a function of time. Okay, basically what's happening, so let's say m and let's take it as 1. Okay, for different x's I have different functions of time. Okay, for example, for x is equal to 2, you will get something like this. For x is equal to 2, so this is at a particular point over here. You get this function with respect to time. So what's happening is that as you apply the temperature step at the boundary, okay, very slowly the temperature at x is equal to 2 starts increasing, and then slowly it resettles at the new steady state. Okay, similarly, if you consider another distance, x is equal to 3, you get a slower response. Okay, and as you go far away, right, x is equal to 4, you get yet another even slower response. Okay, so x is equal to 4 and so on and so forth. Okay, and obviously at x is equal to infinity, right, x is equal to infinity, nothing happens, right, x goes to infinity, you get no response at all at infinity. Okay, you can also check also for fixed time. For example, let's say that t is equal to 10. Okay, now you can also sketch a function with respect to x. Okay, remember this function is both a function of time and space, so you can sketch it with respect to each one of the variables. Okay, so with respect to a fixed time and with respect to x, at x is equal to 0, obviously you start with m is equal to 1 because that is the point where I apply the step function. But as you go far away from that boundary, you get a function that kind of approaches 0. Okay, so this is temperature with respect to x, but at a fixed time. Okay. Now, also in the book, there is kind of a normalization where all of these families of curves at the top can actually be normalized into a single curve. I find that not very intuitive and kind of confusing, but still, I'm going to put it for completeness. But I find this family of curves sketch much more informative, much more intuitive to understand as compared to this normalized version. Okay, so all these curves can be kind of summarized into a single curve. If we normalize the time variable, okay, so let this normalized variable be a over x squared times t. So theta is our new time variable, normalized with respect to x. So in this case, we get a function like this. So with respect to theta, so I have 1 over here, m is equal to 1, okay, 0.5. So you get a strange function like this, basically. Sorry, this, I'm not sure whether this was actually m is equal to 1 or simply this normalized function. Okay, so you get basically something like this. Okay, so 1, 2, and so on. Okay, so this is this normalized variable. Okay. Note, we worked actually on delta variables. Okay, around the ambient. Okay, to make the initial condition zero assumption. So the actual temperatures, if you want to really write them, T0T, remember, is TE plus tau 0T, and therefore it is equal to TE plus m times u of t, and therefore TXT is equal to TE plus m times ERFC x over 2 square root of AT. Okay, for x positive and t positive. Okay, so that is our solution. All right, now, so that's kind of the analytic solution of this partial differential equation. Now, what I want to discuss is how we can approximate this as a lumped parameter approximation. Tabii ki. So that's going to be what we call the early pass, okay? What we have discussed is what was called the late pass, and excluding any controller design kind of discussion. But we tried to develop a mathematical model. Obviously, there is no concept of a Laplace transform at this point. There is no concept of a transfer function, okay? But we at least have a solution, a time solution for what's going to be the response like, okay? So the lumped parameter approximation is the early pass approach, which as we will see will result in a higher order ordinary differential equation, okay? So often problems involving partial differential equations cannot be solved analytically, okay? The early pass method can be used to discretize the space variable to result in a higher order ordinary differential equation. So we will divide the model into n interconnected lumped parameter components, okay? So low order partial differential equation becomes either a higher order ordinary differential equation. Order depends on the resolution of discretization, namely n, okay? It really depends on what you choose as your n variable. Also, you can obtain a system of interconnected first order ordinary differential equations. That is what we call the state space model. Okay, so I will do this for our temperature problem, okay? So for our temperature problem, now what's going to happen is that the distributed parameter that we start with, parameter txt becomes ti of t with I1 to up to n, where ti of t assumed to be constant with respect to x over n elements. Okay, the example will make it much more clearer. Okay, so let's put the example with a chosen number. Okay, let's say that n is equal to 3, and we consider our rod, insulated rod. Okay, so here is our example again. So here we have insulation on the sides. In fact, we will not make any infinite slab assumption in this case. We will consider both boundaries. Okay, I will divide this into 3 equal segments. Okay, so at this boundary there will be T in of T. Again, a lumped value at the boundary. Okay, we will have T out of T at this boundary. Okay, we will have obviously a transfer of heat energy Qi, and then heat will be transferred in between the elements Q2, etc., Q3 over here. Each element will have its associated temperature. Okay, T1 of T constant with respect to X within this element, tau 2 of T, tau 3 of T. You see, the X variable has become an index now. A finite number of lumped parameter variables have been generated. Okay, instead of having the temperature being both a function of X and time, now I have tau 1, tau 2, tau 3, which signify the dependence on X, but each one of these variables is a continuous function of time. Okay, again we have cross-sectional area, cross-section area A, and also I have heat transfer coefficients alpha 1, alpha 2, alpha 2, alpha 3. These are both alpha 2 because they are the alpha 1, alpha 3 boundary parameters, and alpha 2 is the inside parameter. This is the heat transfer coefficient, remember. Heat transfer coefficient. Okay. So we have tau E at 0 is equal to 0. 0 initial condition. So we are still working with the delta variables. Okay, working with delta variables around the steady state. Okay, so we have 3 variables, 3 state variables in this case, and we want to write down lumped parameter model equations for each one of them. Okay, so let's try to do this for the initial elements, for the initial left hand boundary element. Okay, what we have, if you remember, we had the heat capacity, okay, which was the area times delta X. By the way, delta X is this distance, right? It's the same for all of them. Delta X, delta X. So area times delta X times the density times the heat capacity Okay, we can call this whole thing as the heat capacitance, d tau 1 of T over dt. Remember, accumulation has to be equal to the inflow of heat minus the outflow of heat. Okay, so that's going to be alpha 1 on the boundary times the area times the temperature difference, T in minus tau 1, tau in minus tau 1. Both of them are functions of time, minus the other boundary over here, right? Alpha 2 times, this time, tau 1 minus tau 2. If I rearrange this, I have delta C d tau 1 of T over dt is equal to alpha 2 times, if I expand that, okay, alpha 1, I will start with alpha 1.
Üstte bir de eğri olacak değil mi? Alfa 2'nin yanında.
Alfa 2'nin yanında da area olacak. Evet, haklısınız. Bakayım. Şöyle yapalım. Alfa 2A. Teşekkür ederim. Alpha 1 tau in minus alpha 1 plus alpha 2 times tau 1 plus alpha 2 times tau 2. Okay, so that is one of the state equations. One state equation. What is the state? That state is the temperature of the first element, tau 1 of T, is one of our state variables. How many of them we have? We have 3 of them for this approximation. What is the order of the system? The order is 3 because we have 3 state equations with 3 state variables. Okay?
Hocam denklemin sağ tarafında bir A olmayacak mı şimdi?
A'ları sadeleştirdik.
Ha, gene delta C dedik de sol taraf, o yüzden.
Haklısınız ama şöyle tanımlayalım. Tamam, doğru, haklısınız. Delta C'yi şöyle tanımlayalım. Area'ya bağlı değil. Çünkü sadeleştiği için iki tarafta. Şimdi doğru oldu. Tamam?
Evet, tamam hocam.
Tamam.
Tamam.
For the internal element, and obviously if you have n larger than 3, obviously there will be many internal elements and you will have to write this kind of an equation for all of them. So delta C again, d tau 2 of T over dt, okay, and that is equal to alpha 2 times tau 1 minus tau 2 minus alpha 2 times tau 2 minus tau 3. We have alpha 2 here because we have alpha 2 for the two boundaries, okay? All the internal boundaries have the same heat transfer coefficient because this is a homogeneous material. So that gives us delta C tau 2 of T over dt, and that is equal to alpha 2 tau 1 minus 2 times alpha 2 tau 2 plus alpha 2 tau 3. So that is the second state equation. Okay, so if this is the first one, this is the second one. Okay, note, you need to keep writing this type of equation for n larger than 3 or for an infinite slab. Okay, so for an infinite slab there will be no other equation. It's gonna just be a number of these equations Okay, but for our case where we have also the other boundary, right hand boundary, we have delta c d tau 3 of t over dt, and that's going to be again alpha 2 times tau 2 minus tau 3 minus alpha 1. Now the outflow again, this time alpha 1 because it's the other boundary with the surrounding environment, tau 3 minus tau out, which is the other boundary variable. Okay, so we have tau 3 of t or dt is equal to alpha 2 tau 2 minus alpha 1 plus alpha 2 times tau 3 plus alpha 1 tau out. Okay, so that's your third state equation. You can see that this number of state equations grows with n. Okay, now let me put all of this into, you see that the derivative of the state variable is written as a function of the state variables. Okay, so that is a state space representation, and furthermore from these equations you can see that this is a linear system. Okay, so let tau 1, tau 2, tau 3 be our state variables, and tau in and tau out in this case are the inputs to the system. Because the system has two interfaces with the outside world, obviously there are two inputs to this system. We can actually apply two transient inputs from the two sides to this system. So let us put this put into matrix vector form, and here is what goes with it. Tau 1 derivative, tau 2 derivative, tau 3 derivative. Obviously we need to divide everything by 1 over we need to divide by delta c because it's a factor on the left hand side, and then we have a matrix times the state variables tau 1, tau 2 and tau 3, and we also have again 1 over delta c, another matrix times the vector of inputs tau in and tau out. What is the size of the second matrix? What is the size of the second matrix over here? You guys tell me.
3 by 2.
3 by 2, right? It has to generate a 3 vector, but it has to multiply a 2 vector. So this dimension has to be 2, and this other dimension has to be 3. Okay, so let's get from our equations what we have. Okay, let's start with the third equation at the last row. Okay, you see that I have over here no tau 1 in this equation, so factor of tau 1 is equal to 0. For tau 2 I have alpha 2 as a factor, and I have minus alpha 1 plus alpha 2, alpha 1 plus alpha 2, a factor of tau 3, and we also have tau out over here, so no tau in, so that's going to be 0, and tau out will be multiplied by alpha 1. Okay, does that make sense? So let's also take a look at this equation, the second equation. You see that we have alpha 2 times tau 1. So I'm going to have here alpha 2 times tau 1. And then minus 2 alpha 2 times tau 2 plus alpha 2 times tau 3 and no input terms. Okay, so over here I will have minus 2 alpha 2 and alpha 2 times tau 3 and no input terms, meaning 0 and 0 over here. Similarly, for the first equation, I don't want to scroll it up, but we will have from the first equation, we will have minus alpha 1 plus alpha 2 times tau 1 plus alpha 2 times tau 2, no tau 3, and I will have alpha 1 times tau in and no tau out term. Okay. Okay. So now let me also give you a note here. Okay. Because from your exam papers, I see that this is a point of confusion. Now, if you had a nonlinear system, okay, you cannot put it into this kind of a vector matrix form. Okay, you can put it in a vector form where you have simply f1 function, f2 function, and f3 function for the derivative of the first state, derivative of the second and third state. Okay, but if you had a nonlinear system, you don't try to put it into x star equals ax plus bu form. Okay, nonlinear systems are left as simply functions, separate functions. Okay, so please, if you see a nonlinear system, don't try to put it into a vector matrix form unless you are being asked to linearize it. Okay, and if you're not being asked to linearize it, don't try to linearize it. Okay, sometimes you are being asked to derive the equations, the nonlinear model of the system. That means just derive the nonlinear model. Don't attempt to linearize it unless you are being asked to do so. Okay, so that's a side note. I have one final note here that I want to discuss with you. Note, we may actually establish the relationship between the lumped parameter alpha i's, as an example, alpha 2, which is the inside variable, and the distributed parameter A, which, if you remember, was equal to lambda over rho times Cp. Okay, so there is a distributed parameter that we have given a different name. Okay, we called it A, and what was the name? The name was, I believe it was called the factor of heat conductivity for the continuous version. And we also have alpha, which we call the coefficient, heat transfer coefficient. So my claim is that we can establish a relationship between A and alpha. Okay, because these are related parameters, but one is specified for the partial differential equation model and the other one is specified for the lumped parameter approximation. Obviously they are related with each other. Let's see how we can derive one from the other. Let's say that delta x is L over N. Okay, and also we need to approximate the derivative with respect to the space variable. So we need to approximate d over dx with a finite difference formula. Okay, So what we will do is we have del tau xt over del x. So we will write this as approximately tau x minus delta x, the previous element, minus tau xt over del x. Okay. Remember that as long as delta x is very small, it doesn't really matter on which side you define the derivative. Okay, you can do both ways. And the second derivative, therefore, you apply this finite difference again, and that results in tau x minus delta x t minus 2 times tau xt plus tau x plus delta x, and t over del x squared. Okay. Again, we need to define tau I of t as being simply the temperature within that interval, I times delta x t, and tau x t being tau I of t for that interval, right? For the interval I minus 1 delta x, x, and I times delta x. So as long as x is within the interval, we associate it with a lumped parameter variable. And therefore, our differential equation, or rather our PDE, becomes d tau I of t over dt, the derivative, is actually equal to a over delta x squared, and you have tau I minus 1 of t minus 2 times tau I of t plus tau I plus 1 of t. So that is the approximation. Okay, and if you compare this, this is inside the slab. Okay, so we have simply written kind of the equation inside the slab. Okay, now here A obviously is given by this lambda over rho Cp. Okay, and if you compare this equation with our lumped parameter approximation equation, okay, with comparing this to our lumped parameter state equation 2, we can obtain the correspondence, which where we have alpha 2 over delta c being equal to simply lambda over rho Cp and delta x squared. Okay, so that is a relationship between the two parameters that we have. All right, so that's all for today. Do you guys have any questions? Arkadaşlar, soru var mı?
Hocam, 3. state equation'da alfa 1 ve alfa 2 var. Ama sanki alfa 1 yerine alfa 3 olmalı.
Aynı varsaydık da o yüzden. Yani inside the slab ile outside of the slab, özür dilerim. Haklısınız. Şunu Ben notlarımda bunu aynı kabul etmişim. Şöyle alfa 1. Ama eğer orası başka bir medium olsaydı da orası alfa 3 olsaydı dediğiniz gibi alfa 1 yerine alfa 3 gelecekti equation'larda. Başka soru var mı? Soru var mı arkadaşlar? Okay, so tomorrow I will start a new topic called multi-loop systems, and that's gonna basically we will discuss different architectures other than the single feedback output feedback loop architecture, and that's gonna be more or less the last topic that we will discuss for this term. So that's gonna take this week and next week, and hopefully we will be able to complete most of it. Okay? Peki arkadaşlar, teşekkürler. Yarın sabah görüşmek üzere o zaman.
Görüşmek üzere hocam.
Görüşmek üzere arkadaşlar. İyi dersler diliyorum.
Hocam.